Okay, look around you. Everything you see, your phone, your desk, that half-eaten sandwich, even the hand you're using to hold it is made of star stuff. But here is the thing. When we look up at the night sky, those little pinpricks of light look static. They look peaceful. They look eternal. But that is a lie. The universe is actually a violent, chaotic factory, and stars are the workers. And just like us, they go through a life cycle. They are born, they have awkward teenage phases, they get jobs, they have midlife crises, where they get really bloated, and then they die. The only difference is that when you die, you might get a nice funeral. When a massive star dies, it rips a hole in the fabric of space-time, so the stakes are a little higher. Today, we are going to walk through the 7 main stages of a star's life. It is a journey that takes billions of years, but we are going to speedrun it right now. Whether it's a massive beast that turns into a black hole, or an average Joe like our sun, they all follow the same script. So buckle up. Stage 1. The giant gas cloud. Every story has to start somewhere. And for a star, it starts in the coldest, loneliest place you can imagine. We are talking about a giant gas cloud. Scientists, being the creative naming geniuses they are, also call these molecular clouds or nebulas. Imagine a region of space that is incredibly cold. We are talking just a few degrees above absolute zero. It's dark, it's dusty, it's mostly made of hydrogen and helium, the 2 simplest elements in the universe. If you were floating in one, you wouldn't see much. It just looked like a thick, dark fog. Now, usually, gas wants to expand. If you spray perfume in a room, it spreads out, right? It doesn't clump together in a ball in the corner. So, for a long time, this cloud just chills out. Literally. It's the Orion cloud complex, just hanging in the void. But gravity is the ultimate buzzkill. Gravity is the force that ruins the chill vibe. All those tiny atoms of gas have a very weak gravitational pull on each other. But if the cloud is massive enough, or if something disturbs it like a shock wave from a nearby supernova, exploding gravity starts to win. The gas starts to fall inward. The center of the cloud gets denser. And as anyone who has ever been on a crowded subway knows, when you pack things together tightly, the temperature starts to go up. The cloud begins to collapse under its own weight. It's not a star yet. It's just a very heavy, getting slightly warmer pile of dust. This is the womb of the cosmos. Stage 2, the protostar. Welcome to Phase 2. Things are heating up, literally, as gravity keeps crunching this gas cloud down. The particles are smashing into each other like a demolition derby. Kinetic energy, the energy of motion, is turning into thermal energy heat. This clump of warm molecules is now called a protostar. Think of a protostar as a fetus. It's not quite a baby yet. It's definitely not breathing air, but it's got the shape. It's getting there. If you looked at a protostar with your human eyes, you probably wouldn't see much because it's still buried deep inside that thick, dusty gas cloud from stage 1. The dust blocks visible light. But if you put on infrared goggles, oh boy, these things glow like a Christmas tree in the dark. They are radiating heat. This is a chaotic time. The protostar is greedy. It is sucking in more and more gas from the cloud around it, growing fatter and hotter. It hasn't started the nuclear engine, yet it's just getting hot because of the pressure. It's like rubbing your hands together to make heat, but on a cosmic scale. And here is a fun fact. A single giant gas cloud doesn't just make one star. It's usually a litter. Depending on the size of the cloud, you can get dozens or even thousands of protostars forming at once. It's a stellar nursery, but it's about to get messy. Stage 3. The T-Tauri phase. Okay, so the protostar has been eating gas and getting fat for a while. Now we enter the T-Tauri phase. This is the rebellious teenage phase of the star. At this point, the star has stopped sucking in mass. It's basically said, okay, I'm full. But it is unstable. It is violent. It's throwing tantrums. A T-Tauri star is technically a star, but it's not burning yet. It doesn't have that nuclear fire in its belly. It's just shining because it's collapsing and releasing gravitational energy. But because it's a teenager, it has to make a scene. T-Tauri stars have massive solar winds. They blast material out into space at insane speeds. This is actually really important. Remember that leftover gas surrounding the star. The T-Tauri winds blow a lot of it away. It clears the room. It's like the star is shouting, "Give me some space." This phase lasts for about 100 million years, which sounds like a long time, but in space years, that's like a blink of an eye. The core is getting hotter and hotter. The pressure is building and building, until finally the temperature hits a critical point, roughly 15 million degrees Kelvin. And that is when the magic happens. Stage 4. The main sequence. This is it. The star has graduated. It got a job. It bought a house. It is a productive member of the galaxy. We call this the main sequence. This is the stage where our sun is right now. If you like being alive, you should be a big fan of the main sequence. Here is what is happening. The core of the star is finally hot enough and dense enough to start nuclear fusion. This isn't chemical burning, like a wood fire. This is slamming hydrogen atoms together so hard that they fuse into helium. When this happens, a tiny bit of mass is lost. Where does it go? It turns into pure energy. E equals mc squared stuff. This energy pushes outward. Now, pause for a second. This is the most important concept in the life of a star. It's a tug of war. On one side, you have gravity pulling everything inward, trying to crush the star into a tiny dot. On the other side, you have the energy from nuclear fusion pushing outward, trying to blow the star apart. In the main sequence, these two forces are perfectly balanced. It's a stalemate. The star is stable. It shines steadily. It's reliable. This reaction is exothermic, which is a fancy science word for it gives off way more heat than it takes to start. It is the ultimate free energy generator. A funny thing about stars. Small stars sip their fuel slowly. They can live for trillions of years. Big, massive stars. They are the rock stars. They live fast, burn bright, and die young. They guzzle their hydrogen fuel like an SUV getting 2 miles to the gallon. Our sun is about halfway through this phase. It's been doing this for 4.5 billion years. And it has enough fuel for another 4.5 billion years. So, you don't need to panic about the sun going out tomorrow. You have plenty of time to procrastinate on your homework. Speaking of burning bright and running out of energy, let's talk about your attention span. I know you're re-tempted to click away to watch a video of a cat falling off a table, but don't, because we haven't even gotten to the explosions yet. Also, if you are enjoying this journey through the cosmos, do me a solid. hit that subscribe button. If you don't subscribe, I'm not saying a black hole will swallow the Earth, but why take the risk? Okay, back to the science. Stage 5. The red giant, all good things must come to an end. Eventually, the star runs out of hydrogen fuel in its core. The tank is empty. The fusion stopped. Remember that tug-of-war we talked about? Gravity versus energy. Well, the energy side just dropped the rope. Gravity instantly starts winning. The core of the star collapses inward. But this collapse creates a weird side effect. As the core gets squashed, it gets incredibly hot, hotter than ever before. This heat radiates outward to the upper layers of the star, which still have some hydrogen left. These outer layers start to fuse, and the heat causes the star to bloat. It expands and expands and expands. The star becomes a red giant. It turns red because, as it expands, the surface cools down a bit. But cool is relative, it's still roasting. When our sun reaches this phase, it is going to get so big that it will swallow Mercury. It will swallow Venus, and it might even swallow Earth, if humans are still around in 5 billion years. I hope we have figured out how to move, because the property values on Earth are going to plummet. Stage 6. The fusion of heavier elements. Inside the core of this bloated red giant, things are getting desperate. The star is trying to survive. It's looking for anything to burn. It has run out of hydrogen, so it starts fusing the helium ash that has been building up. It fuses helium into carbon into neon, then oxygen, then silicon. It's like a frantic chef running out of ingredients. We're out of hydrogen. Cook the helium. Out of helium. Cook the carbon. Each stage happens faster and faster. The star burns hydrogen for billions of years. It burns helium for a few million. It burns carbon for a few thousand. By the time it gets to silicon, it burns through it in a matter of days. But then it hits a wall. The element iron. Iron is the star killer. Fusing iron doesn't create energy. It consumes energy. It's an energy vampire. As soon as a star tries to fuse iron in its core, the engine stalls. The outward pressure disappears completely in a fraction of a second. Gravity, which has been waiting for this moment for billions of years, finally wins the war. Stage 7. Supernova and planetary nebulae. This is the finale. How the star dies depends on how fat it was to begin with. Scenario A. The average Joe like our sun, if the star is small or average. It doesn't have enough gravity to fuse iron, so when it runs out of fuel, it doesn't explode violently. It just sort of ... sneezes. It gently puffs its outer layers off into space. This creates a beautiful, glowing shell of gas called a planetary nebula. Confusing name. It has nothing to do with planets. Astronomers just suck at naming things. In the center, The core remains. It shrinks down into a white dwarf. This is a dead star. It's incredibly dense, squeezing the mass of the sun into the size of the Earth. It's hot, but it's not generating new energy. It's just slowly cooling down, like a dying ember in a campfire. Eventually, after trillions of years, it will go dark and become a black dwarf, a cold, dark diamond in the sky. Scenario B. The heavyweight champ, massive stars. If the star is massive, we're talking 8, 10, 20 times the mass of the sunlight. Doesn't go quietly. When the iron core collapses, it happens at 25% the speed of light. The core implodes, then bounces back. Boom. Supernova. This is the biggest explosion in the universe. For a few weeks, a single supernova can outshine an entire galaxy of billions of stars. It blasts all those heavy elements, the carbon, the oxygen, the iron, the gold out into the universe. Remember when I said we are made of star stuff? This is where it comes from. The calcium in your bones, forged in a star and blasted out by a supernova. The gold in your jewelry, supernova. You are quite literally the debris of a cosmic explosion. The remnants after the supernova, what's left? If the star was big, the core becomes a neutron star. This thing is so dense that a teaspoon of it would weigh 1 billion tons. It spins wildly, shooting beams of radiation like a lighthouse. If the star was truly massive, the biggest of the big, gravity crushes the core down to a single point. Infinite density, 0 volume. A black hole. A region of space where gravity is so strong that not even light can escape. It is the ultimate ghost of a star, eating everything that gets too close. So there you have it. The 7 stages. From a cold, boring gas cloud to a glowing protostar, through the rebellious T-Tauri phase, into the stable main sequence. Then comes the bloating of the red giant, the desperate fusion of heavy elements, and finally spectacular death of a supernova or the quiet retirement of a white dwarf. It's a cycle. The gas blasted out by the dying star eventually clumps together to form new clouds, new nebulas, and new stars. The circle of life, but with more nuclear fusion and less singing lions. Next time you look up at the night sky, don't just see little twinkling lights. See them for what they are. Massive nuclear furnaces, fighting a war against gravity, destined to one day explode and seed the universe with the ingredients for life. And hey, if a star can keep it together for a few billion years, under that much pressure, you can probably handle your Tuesday.